Welcome. In this video, we are going to explore practical optimization problems solved using linear programming. This project stems from a term paper assignment where the focus was on tackling a realistic logistics challenge. Specifically, we will explore how to efficiently manage vehicle routing, inventory, and delivery scheduling across multiple time periods and locations. And the problem involves multiple vehicles delivering different products to customers while minimizing costs like routing, inventory holding, and penalties for unmet demands. We will also account for operational constraints such as vehicle capacities, delivery time windows, and route optimization. And throughout this video, I will guide you through the steps of building the solution from scratch using Julia and the Jump package powered by Higgs Solver. We will break down the code section by section so you can understand both the logic behind it and the decisions we made while modeling the problem. Okay, let's start by setting the foundation for our optimization model. And the first step is to import the necessary Julia packages. We are using Jump, a powerful modeling library for optimization, along with Higgs, our solver that will handle the optimization computations. And additionally, linear algebra is included for matrix operations, and data structures is used for advanced data handling. Alright, next we define a structure set of parameters using a struct named problem parameters. You can see here in line 5. And this allows us to neatly organize all critical constants required for the model, and here we are specify m, which is a large constant often used in linear programming for constraints involving logical conditions. And here max route length representing the maximum allowable route length for any vehicle. Min delivery defining the minimum delivery quantifier for any route to ensure efficient operations. Here fixed vehicle cost, what is that? It stores the fixed cost associated with each vehicle. Time window, a dictionary that assigns time constraints to each node or location. And service times, representing the time required at each node to perform deliveries or pickups. Alright. After that, we initialize the optimization model using a Higgs optimizer, which we will solve the problem we construct. And we set up the basic data for our problem. Nodes represents all the locations in the network, and node 1 is a depot, while node 2 for our customer locations. And products defines the two types of products that will be delivered. Time periods represents the planning horizon divided into 3 time periods. Vehicles refers to the 2 vehicles available for deliveries. Finally, we specify the parameters for the model, and vehicle capacity is set to 50-50. What is that? It meaning each vehicle has a maximum capacity of 50 units. And we initialize the params structure. Here you can see with values for big M, the maximum route length, the minimum delivery quantity, fixed vehicle costs, time windows for deliveries, and service times for each node. Okay. Here we will define the demand data, cost parameters, and decision variables for our optimization problem. We begin with the demand. You can see here it's organized in a dictionary format. Each key represents a pair of product and customer node, while the associated value is a list of demand values across 3 time periods. And for instance, 1, 2 specifies the demand for product 1 at customer node 2, which is 0, 10, 15 over the 3 periods. And this structure helps us capture the dynamic nature of demand across different locations and times. Okay, here we define the cost parameters, and holding costs are set as 3, 2. I mean 2 and 3 here, indicating the per unit cost of storing each product in inventory. Product 1 incurs a holding cost of 2, while product 2 incurs a cost of 3. Penalty costs for shortages are uniform across all customer nodes set at 50-50, 50-50, and these values impose a significant penalty if customer demand is not fully satisfied, encouraging the optimization model to prioritize deliveries. And routing costs are represented as a matrix where each cell captures the cost of traveling from one node to another. For example, traveling from node 1 to node 2 incurs a cost of 10. To emphasize the importance of efficient routing, we have doubled all values in the matrix by multiplying it by 2. You can see here. And decision variables here, they are core components of the optimization. And X here, what is that? It is a binary that determines whether a vehicle travels between two nodes during a specific time period, and Y, another binary variable that indicates whether a vehicle visits a specific node during a specific time period. Q, a continuous variable representing the quantity of a product delivered by a vehicle to a node in a given time period. And here I, what is that? The inventory level of each product at each node during a specific time period. As it is a shortage level at each node during a specific time period. Arrival time, the time when a vehicle arrives at a specific node during a time period. Route duration, the total duration of a vehicle's route in a given time period. Use vehicle, a binary variable that determines whether a specific vehicle is used in the operation. And U, a variable used to enforce the MTZ subtour elimination constraints, ensuring that the routes do not form disconnected loops. Alright. Here, vehicle usage constraints. To ensure that the model accurately reflects the use of vehicles in operations, we define constraints on their usage. And the key idea here is to link the binary variable use vehicle. Here you can see key to the visits made by a vehicle K to the depot. And the first constraint enforces that the sum of visits to the depot by vehicle K across all time periods cannot exceed a large number m times the use vehicle K variable. This ensures that if a vehicle is not used, it doesn't make any trips. And the second constraint ensures that if a vehicle is used, it must visit the depot at least once across all time periods. And these constraints collectively control the activation of each vehicle. And objective function here, it is a key to solving optimization problem. And the goal is to minimize the total cost incurred during operations, and the objective function comprises 4 major cost components. And I'm looking first, inventory holding costs. These are calculated as the product of the holding cost for each product, the inventory levels, and the respective time periods. And routing costs. This accounts for the cost associated with moving between nodes, weighted by the distance between them and the binary routing variable x. And penalty costs. These are applied for shortages at customer nodes and ensure that the model penalizes unsatisfied demand. And fixed vehicle costs. This represents the cost of activating a vehicle and are applied whenever use vehicle key is set to 1. Okay, what's that? To manage inventory effectively, we establish a balance constraint for each product at every node and time period, and this ensures that the inventory at time t, you can see here t, equals the inventory at the previous time period plus the quantity delivered to the node during time t by all vehicles. And from this sum, we subtract the demand for that product at the node during time t. And this constraint guarantees that inventory levels are updated dynamically based on deliveries and demand. If the demand exceeds the delivered quantities, the shortage is captured by the penalty cost. Okay. Here initial inventory constraint. What is that? We begin by defining the initial inventory levels for each product at every node in the first time period. The logic here is straightforward. The total inventory at the start equals the sum of quantities delivered by all vehicles to that node in the first period. And this ensures that all initial stock is explicitly accounted for, providing a solid baseline for subsequent calculations. And I'm looking, what can I say? The constraint is expressed as like that. Here you can see. Okay, demand satisfaction. Demand satisfaction is a critical part of any supply chain or vehicle routing problem. These constraints ensure that for every node, the total quantity delivered by all vehicles meets or exceeds the demand for each product in every time period. And if there is any shortfall, it is accounted for using the shortage variable S and IT. That's it. By including shortages in the model, we allow flexibility but penalize such occurrences in the objective function to prioritize meeting demands whenever possible. And here the constraint is represented as like that, bigger than demand. Okay, routing constraints here. What happens here? Each vehicle must start its route at the depot, and it is node 1, and return to it by the end of the time period. And the sum of all outgoing and incoming routes at the depot is tied to the binary variable, which indicates whether a vehicle is active at the depot, and y k1t is a binary variable here. Okay, here flow conservation, what is that? This ensures that for any customer node, the sum of all incoming routes equals the sum of all outgoing routes. And additionally, this sum is equal to the binary visit variable, which indicates whether a vehicle visits a specific node in a particular time period. And here y and key it is a visit variable. And that's okay, I think. And here, fourth, vehicle capacity constraints. It ensures that the total quantity of products delivered by each vehicle to customer nodes doesn't exceed its capacity during any given time period. This maintains operational feasibility by respecting the predefined limits of the vehicles. And what happens here, the constraint is written like that, some key, Q, key, P, I, T, for etc. Other things, vehicle capacity here. And this guarantees that no vehicle carries more than its maximum capacity. 5 here. This constraint ties the quantity delivered by a vehicle to whether it visits a particular node. If a vehicle doesn't visit a node, it cannot deliver any product to that node. And this is achieved by the following formulation. Again, sum Q, key, P, I, T, etc. And this, here. And this linkage ensures logical consistency in the model, preventing deliveries without a visit. And here, MTZ subtool elimination. And the MTZ Miller-Tucker-Zemlin constraints are used to eliminate subtours in the routing solution. And subtours occur when a vehicle forms a closed loop without connecting to the depot or fulfilling all deliveries. This is managed by the following constraints like that. And here U represents any auxiliary variable that helps track the order of visits. The logic prevents forming isolated loops, ensuring a connected and feasible route for each vehicle. And 7, what is that? This constraint guarantees that all custom nodes are visited at least once during the entire planning horizon. And it is represented as like that. And this ensures that no customer is neglected, fulfilling the basic requirement of the routing problem. And 8, here, in our model, we need to ensure that each vehicle, after completing its route for a specific time period, returns to the depot. And this is essential for maintaining the logical flow of the delivery operation. And again, the constraint is expressed as like that, nodes. And this means that for every vehicle key at every time period t, the number of trips starting from the depot must equal the number of trips returning to the depot. And this ensures that the routes are balanced and all vehicles start at the same point. Okay, solution printing function. And to make sense of the solution generated by our model, we have implemented a comprehensive solution printing function. This function does several important things. For example, objective value display. And I'm looking. It begins by printing the objective value of the solution, which represents the minimized total cost of operation. Here, objective value, round objective value model, digits 2. Okay. Next, it calculates and displays the breakdown of the total cost into 4 components. Routing costs, the total cost of all routes taken by the vehicles, calculated like that. And holding costs here, the cost of holding inventory at various locations computed for each product and node. Okay, and penalty cost here, what's that? The cost incurred due to the shortages calculated as like that. Penalty cost I multiply value S and IT. Fixed vehicle cost here, and the fixed cost associated with using each vehicle determined by params dot fixed vehicle cost key multiply value use vehicle key. And each of these costs is calculated and summed up across the entire planning horizon to give a detailed view of where the expenses lie. Okay, what is that? That's done. Okay, and what is that? Here we transition into the part of the code responsible for producing detailed routing and deliver information for each time period. And this segment provides an intuitive visualization of the operations planned for every, each vehicle. And we start by iterating through the specified time periods. For each time period, we print the header and introduce a Boolean flag called period. Deliveries exist to track whether deliveries occur in that time frame. That's okay. And for each vehicle, the code checks whether it is active in the given period by calculating the sum of route variables. I mean x, key, I, j, t here. And if the vehicle is indeed active, we set period deliveries exist to the to true and proceed to generate its operational details. Okay, and I'm looking. The first task is to determine the vehicle's route, and starting from the node 1, we iteratively traverse to the next node using the X decision variables, marking visited nodes along the way. And this process continues until all relevant nodes are visited, after which the vehicle returns to the node 1, and the complete route is printed as a sequence of nodes, and the cost of this route calculated and displayed. And I'm looking. We dive into details of, dive into details deliveries made by this vehicle during the given time period. For each customer node and product, the delivered quantity is derived from the Q decision variable. Any non-zero deliveries are printed, providing a comprehensive view of the vehicle's logistical activities. And if no deliveries are made in the period, the flag period deliveries exit ensures that this information is explicitly conveyed. And that's okay. And now we will look at printing inventory levels. Okay, and I think it is final part of our code. And where are we? Something printing position, not that. Okay, again here, printing inventory loss. All right, what happens here? Let's look. First, the inventory levels for each time period are calculated and presented. And this part of the script iterates through all nodes and products, checking if any inventory remains at the end of each period. It ensures clarity on whether inventory management meets the demand requirements and evaluates potential excess. Next, shortages part. You can see here the shortage calculations are processed, and the model evaluates whether the deliveries to customers were insufficient in meeting the set demand levels. In any shortage occur, the time period, node, and product impacted are logged, providing insights into where adjustments may be necessary. And following that, the cost breakdown section offers a comprehensive view of how the total cost is distributed across routing costs, inventory holding costs, penalty costs, and fixed vehicle costs. And these values are important for evaluating the efficiency of the solution, as they indicate the financial impact of the decisions made by the optimization algorithm. Lastly, the model solution is printed if it meets the optimality criteria. If the problem is infeasible or unbounded, the script ensures to communicate this, emphasizing the need to revisit constraints or data inputs. And okay, code is done. And we'll look at our outputs now. All right. And what happens here? The solver we used is Higgs, here, version 1.9 and 0, and efficient optimization solver for linear programming and mixed integer programming. Okay, and the initial appraisal phase reduced the problem size significantly, and from 155 rows, 192 columns, and 629 zeros, it optimized down to 145 rows and 176 columns and 598 non-zeros. And this pre-processing step is critical, as it simplifies the problem without altering its essence, making it easier to solve. Okay, and what is next? The final model consists of 145 constraints to handle routing, inventory capacity, and delivery balance, and 176 variables, out of which 104 are binary, ensuring decisions like vehicle usage and route assignments are appropriately modeled. Okay, and branch and bound process. Here you can see, let me select for you so that here the solver uses the branch and bound method to explore feasible solutions, and the table breaks down this process and notes processed. And what is that? The solver evaluates, I'm looking, 41 nodes to find the optimal solution. Okay, and what is next? Best bound and best solution. This matrix converged at 430, indicating that the solution is both feasible and optimal with no gap, and the tolerance is 0.01%, ensuring high precision. And how about LP, I mean linear programming iterations, and a total of 5,382 iterations were required, with the majority allocated to strong branching and heuristic methods. and this demonstrates the complexity and computation effort involved. That's okay. And we will look at solving report here. What happens here? Here the critical highlights from solving report and status. The solution is optimal. You can see objective value. The total cost of the optimized solution is 420, and this includes routing, holding, shortage penalties, and vehicle fixed costs. Okay, and timing. The entire process completed in 0.75 seconds, showcasing the efficiency of the Higgs solver, even for complex models like ours. And what can I say? As is there anything? Sorry, just looking. I think it's okay. And now what is next? Here we will look at other things. Again, objective value here. The solution yielded a total cost of 430, and this is the sum of all incurred costs, including routing costs, fixed vehicle costs, holding costs, and penalties for shortages. And the breakdown of this total cost will be detailed shortly. And we analyze the deliveries across time periods and time one here. No deliveries were made during this period, and this outcome aligns with the optimization model, which strategically decides not to deploy vehicles when demand or cost consideration suggest otherwise. And time period 2, what happens here? Vehicle 1 was assigned to route 1421, starting at ending at node 1. And the route cost for these operations was 8 units. Deliveries included node 2 product 1 10, node 2 product 2 5 units, node 5 sorry, what's that? Node 4 product 1 15 units, node 4 product 2 5 units, and okay, vehicle 2 followed the route 131 with a route cost of 6 units, delivering like node 3 product 1 20 units, node 3 product 2 10 units, and time period 3 here. What happens here? Vehicle 1 traversed the route 1241, incurring a route cost of 80 units, and completed the following deliveries: node 2 product 1 and 15 units, node 2 product 2 and 10 units, node 4 product 1 10 units, and same things. And here vehicle 2 continued its efficiency with the same route as the previous period, and 131 at a cost of 6 units, delivering node 3 product 1 5 units, node 3 product 2 5 units. And here inventory levels. Across all time periods, no inventory was held at any node, and this indicates that all products were delivered just in time to meet demand, avoiding additional holding costs. Shortages. No shortages were recorded during any time period. This confirms that the optimization successfully ensured all demand was met without penalties. And cost breakdown here, the total cost of 430 is divided as follows. Routing costs, 280 units, holding cost 0, I mean no inventory was held, penalty cost 0.0 units, I mean no shorts occurred, and fixed vehicle cost 150 units. And that's all for this project. Thank you for listening. See you in the next video.